Since time immemorial, we have built our own cosmological model based on observation, theories, and mathematical foundations, and there are indications that the universe does not agree completely. You may be aware of the cosmological crisis, which arose due to discrepancies in the measurement of the age of the universe by different methods. Cosmologists are puzzled by these inconsistent results, a situation that has been exacerbated by recent images captured by the Webb Space Telescope. The universe is undergoing an expansion, with distant galaxies moving away from us. One method of calculating the expansion rate is based on the cosmic microwave background, which gives us a certain rate. Another method involves observing the brightness of distant supernovae, comparing their expected brightness with the observed brightness to estimate the expansion rate at the time of the supernova. This method, known as a standard candelas, shows a different expansion rate. The expansion rate of the universe is consistently referred to as the Hubble constant. The discrepancy between the results of these two methods is known as the Hubble tension, which is at the heart of the cosmological crisis. However, this is not the only problem. There is a new critical situation in the cosmological realm that seems to be a distant variant of the crisis facing cosmology. It is like that distant relative to which we hardly pay attention. Years have been spent developing a scientific theory about the universe, and now that theory is coming under scrutiny. But that's how we move forward. That's how science progresses. When we look up at the sky, away from the cities and places that obstruct starlight, we see the Andromeda galaxy as a tiny dot in the midst of countless stars. This is because the universe is full of stars and galaxies, but the question is, how much of this matter actually occupies any part of the universe? How much matter is there really? These are simple questions, but their answers are far from straightforward. This dilemma persists largely because of the current cosmological observations, which do not agree on the distribution of matter in the universe. This discrepancy has given rise to the S8 tension, also known as the discomfort associated with the measurement that now troubles us. The S8 tension is a measure that evaluates the clustering or accumulation of matter in the universe. To simplify it, think of the universe as a huge jigsaw puzzle, where the pieces represent matter dispersed in space. Space scientists seek to understand how this matter is distributed and how it clumps together. There are two approaches to measuring this. First, an accurate measurement is made through observations such as gravitational lensing. Gravitational lensing is a phenomenon where the immense gravitational pull of massive objects, such as black holes and galaxies, acts like cosmic magnifying glasses, bending and distorting the light from distant objects that would otherwise be invisible. This phenomenon gives us a broader view of the vast universe. However, the SA value derived from the second approach, based on the standard model of cosmology using measurements of cosmic microwave background radiation, differs from observational derived values. This discrepancy is at the heart of the mysterious SA tension, where there is clearly an element that defies our understanding, challenging the agreement between numerous theoretical observations and hypothetical entities that support these theories. To unravel this enigma, one of the world's most powerful supercomputers has been used to perform cosmological simulations. The magnitude of this project is evident when considering that part simulations required more than 50 million hours of computation, distributed among the 30,000 processors of the supercomputer at Durham University in the United Kingdom, nicked Flamingo. This project, with its complex acronym denoting the complete interpretation of large-scale structures and detailed mapping of the sky for the interpretation of next-generation observations, stands out not only for its immense size and resolution, but also for its comprehensive approach, which is distinguished from previous simulations focused solely on modeling dark matter. Flamingo goes beyond considering gravity alone, for white dark matter makes up most of the mass of the universe. Ordinary matter, despite representing only 1/5 of the total mass, exerts a significant influence on the distribution of matter on smaller scales. Factors such as galactic winds, driven by supermassive black holes and supernova explosions, can affect the formation and evolution of galaxies. Unlike previous simulations that focused solely on dark matter, Flamingo incorporates and tracks ordinary matter, recognizing that although dark matter dominates gravity, the role of ordinary matter cannot be underestimated. Despite remarkable advances, these simulations represent a step forward in our understanding of the formation of celestial bodies, such as the Milky Way and the Andromeda Galaxy. Flamingo, on the other hand, fails to explain the sparse accretion of matter in the present-day universe, which means that it does not solve the very problem it was created to solve. For example, to help resolve the SA tension. In other words, the Flamingo simulation suggests that something is deeply inconsistent with our standard model of cosmology. Moreover, they contradict observations made by the Webb Space Telescope and other observatories regarding the distribution of matter in the universe. Although these simulations provide detailed insight and consider the role of supermassive black holes, they fail to accurately predict the actual distribution of matter. They indicate that galaxies evolved in a certain way, but there is a mismatch. They predict that they are 7% more densely clustered than they actually are. Although this new computer simulation is much more detailed and covers aspects such as the impact of supermassive black holes, it also does not match reality, indicating 5% more crowding than observed. This is a major breakthrough for science, as it shows us that there is still much to be discovered. This discrepancy indicates that significant revisions to our current cosmological model are required. This process is typical in science, anticipating a major challenge that is already looming on the horizon. This mismatch between computational simulation and actual observations has provoked intense reflection in the scientific community. The existence of 5% more crowding than predicted raises fundamental questions about our understanding of the cosmos. Researchers are at a crucial juncture, facing the need to revise and adjust our current cosmological framework to account for these new observations. Science, at its core, thrives on the discrepancies between theory and observed reality. It is a powerful reminder that even with advanced computational models and rigorously tested theories, the universe always has surprises in store. These moments of dissonance between our predictions and what we find in the cosmos are the engines that drive innovation and scientific progress. Exciting and challenging times lie ahead for cosmology and astrophysics. Scientists are engaged in the task of evaluating and reformulating theories to accommodate these new observations, seeking to better understand the fundamental nature of the universe. This process of revision and change is inherent to science progress and often marks the beginning of revolutionary discoveries that profoundly alter our perception of the cosmos. What new horizons will stars explore in the future? What revelations await us in the vast firmament, ready to unveil secrets as yet unknown? If you liked the video, we invite you to show your support by leaving a like and subscribing and activating the notification bell, as this motivates us to continue creating content. Thank you so much for watching, and I'll see you in the next one.